All right, well, welcome. I hope you all had a good spring break. So we have a bit of a change this time. We actually have Linda Antas, who is a professor in the School of Music, who's going to be giving us a presentation on sonification of GPS. So, yes, that sort of fits within the data science theme. So with that, I'm going to let you introduce yourself more.
Hi, everybody. I'm trying to get my computer. I don't have one of those fancy remotes, so I'm trying to get my computer closer to the screen, lest I need to gesticulate. Hi, I'm Linda Antas. I teach the music technology program here. My doctorate was from the University of Washington in Seattle, where they have a lot of really fascinating audio technology work going on, and my other two degrees are both from the University of Illinois, which is also quite prominent in the electroacoustic or electronic sounds composition field for quite a long time. So the project, this is a work in progress, and I guess my biggest caveat is that the premiere isn't until 3 months from now. So, you know, I have some examples we can hear. I'm not doing that badly for making that deadline. I collected various kinds of GPS data last summer, primarily hiking, although my sister and her spare kayak showed up at one point in the middle of the summer, and I said, I have the kayak, I have the GPS, let's just take the data and maybe we'll make something out of it and maybe we won't. It actually ended up being some of my favorite data. So when we talk about sonification, it is also known as auditory display. And it uses nonverbal sounds to represent numerical data and provide support for information processing activities of many different kinds. So, to make that a little more clear with examples, basically using audio data where perhaps the visual data will just become too complex, too many layers on your graph, too many colors, too many squiggles, and that sometimes it's actually easier to listen to your data than to look at your data. So one early example is the stethoscope, where the doctors are trained to listen to heartbeats, your lungs rattling around, and come to some kind of diagnosis about what's happening inside you through that. A Geiger counter, where the number of ticks represents what your reading is on the radiation. And this has also been done, my project is certainly not the first in the world of music. In 1970, the composer Charles Dodge, who taught at Columbia and later Dartmouth, wrote a piece that sonified the Earth's magnetic fields. It is called the Earth's magnetic field. So the idea of sonifying for purely musical outcomes is, again, not new. And I'm going to talk a little bit about the approach that you might use if you were sonifying for science versus science-inspired art. So one of the problems in the field, and again, this is by Smith, mainly does the sciencey end of it, but that a lot of the mappings where you take, layer A and you're mapping that onto musical parameter of pitch, and you take layer B of data and you're mapping that onto making loudness or volume, is that it's sometimes done arbitrarily, and the resulting sound is often unpleasant and usually lacks any natural connection to the data. So the idea that, one would think that different kinds of data should sound different from one another. And his second point in a later paper that sometimes the sounds produced can be unpleasant. Well, it's all in how you map it. And obviously, if I'm going for the musical results, I'm going to be a little less concerned with certain aspects of the mapping than a scientist should be if they're doing it for scientific reasons. So the most straightforward way of doing any kind of sonification is that you take one dimension of your data and you map it onto a sonic parameter. So you're going to see a lot of examples where I do it the fairly obvious way, and I will map altitudes onto pitches. So the higher up the altitude, the higher the pitch. And you can also get your speed for each leg off the GPS, which I map onto musical durations, or how long until the onset of the next musical event. So they referred to the problem that Smith was kind of pointing at as the mapping problem. How do we map or relate the different parameters into data onto the sonic parameters? And again, in the field, that's a pretty big deal. But to talk myself down, I thought, when do we have a problem of any kind? Period. Doesn't matter whether it's sonification or music or life, right? One is when we can't easily compare the outcomes of multiple decisions, right? You'll never know what would have happened today if you did X, Y, and Z because you only have one this morning and it's a done deal, right? We also tend to have problems when we don't know what we want as results. And automatically, I felt much better after coming to that conclusion because when you're working like this, all you have to do is change some code to hear what that data would sound like if it had been done differently, if you had done the mappings differently. So no problem, right? We're musicians, we're very neurotic, we rehearse hours and hours a day. So to sit there and write code and run new algorithms with different notes or different ways of sonifying, not a big deal. Not going to worry about it. Also, we have a problem when we don't know what we want as results. And again, I'm actually writing this piece for a very well-known cellist that lives in New York named Madeline Shapiro. And I want to write Madeline a piece that she will love to play on her cello. That's what I want. That's my result that I want. I want it to be musically interesting for the performer and for the audience. So the big question then is, to what extent can or should the data be shaped? How should it be tweaked at all? And there are certainly people doing this kind of work that would say, absolutely not. You plug your data into your parameters, voila, it's music. And yes, it is, definitely. But is it the kind of piece that Madeline Shapiro is going to want to play over and over and over again? I'm not convinced. So my solution, and then there comes that point in any project where you get to a certain point, you look at your initial data, and you go, oh crap. Because when you think about what I did, I took a bunch of hikes in the mountains. They tend to go up and then they come down. And that's really boring, potentially, right? For a melody to just go up and then come right down. If you think of even the most simple of all melodies, they tend to go up and they come down eventually, usually, but they take a left turn or two on their way back down, right? So if you even think of the theme from Beethoven's Ninth, da 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 da. So it goes up and it comes down, but it certainly doesn't go da 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 da. That's boring, right? Right. So I wanted to take my mountain data and still make it, still have it be what it originally is, but to sound more interesting. So, there are different gradations of sonification, and technically it's only sonification if you do hear the original data. So I really want to stick to it being sonification, to following fairly closely the original GPS data, but I also want it to be interesting musically. So, I'm so far adding, like I say, left turns here and there to make the GPS data a little more interesting. And I'll play you several examples of that in a minute. Since we are in a CS department, I'll tell you about the tools that I'm using to do this. My first application is called Comet Music. Actually, the more recent rendition of it is unfortunately called Grace, which I know is another coding language, and it makes it really confusing. But I'm talking about CM Grace, Common Music Grace, which stands for Graphical Real-Time Algorithmic Composition Environment. That's the Grace I mean. All of these apps I'm going to mention 3. They're all available on SourceForge, and they're all 100% free. They are supported and built by developers in the community. So you want something done, you can do it yourself and have them add it to the next release, or they might just do it for you. So Common Music is implemented in C++. It has the capability to send data out to other sound synthesis environments. It can also generate things as MIDI files, as open sound control, so it's extremely flexible. The actual coding that you're doing is in Scheme, And it's a version of Scheme called S7, which was developed by Bill Shopstack at Carmen, the Center for Computer Research in Music and Acoustics, which is at Stanford University. And it was begun by Rick Taube at Stanford in the 1990s. He's currently at the University of Illinois. For sound synthesis, my go-to app again for free on SoundForge. You can run it from a command line. You can run it in a Python-based GUI called CSoundQT. Is a music synthesis and signal processing language, text-based again. Historically, it's related to Max Mathews' 1957 music series of programs. And this particular iteration was developed by Barry Vercoe at MIT. Currently runs on a variety of mobile devices, Android, iOS, and even Raspberry Pi. So some really great applications you can download for free. They have really great support lists. If you write into the forum, you're going to have an answer. I've never seen it take more than an hour. It's pretty amazing. Also, Super Collider, I don't have any examples whipped up, but it is, again, freeware. Kind of specializes in doing real-time transformations of input signals. So I can play into a microphone and have my computer sound backup generated in real time, which is a really amazing way to work. And its creator, Jim McCartney, is currently working for Apple. So I have hikes that I sonified from the Bridgers, the Gallatins, the Crazies, afloat down the Ruby River. And I don't have any to show you now, but Common Music actually does a neat thing where it'll follow your mouse position, mouse X and mouse Y. So, the project was really inspired by when I looked at the mountains. And it started in Seattle. I'd be there in the lab 12 hours a day because I didn't have a computer at home, and looking at waveforms on the screen all day. And I'd look out the bus window and I'd see the Cascades or the Olympics and think waveforms, even though they're not waveforms, right? They're mountains. So when I look out my studio window here I live in Belgrade, I see the Bridgers. And I've always seen musical trajectories in the profiles of mountains. And there's kind of this, kind of at odds with myself that I really love technology. I do it all day. I teach music tech. I use technology to make my own music. And yet I start to feel really insane when I don't get out into the wilderness on a regular basis. So a lot of this was my wanting to kind of combine those two loves and see if I could, some way get a slightly healthier work-life balance. So that's just kind of like the program note for this piece. But all right, so the first hike I'm going to talk about by the trajectory is actually one of the more interesting ones. This is Ross Pass, and this is, we have some of those kind of lobes that come off the Bridgers, which are mainly north-south, and then you get heading west, you get some kind of side mountains. So that's what these are. I think this is Jones Creek, and this would be Truman Gulch right about there, and that's where the campsite was. So that's, the green line there is your altitudes, and your blue lines are the speeds. So your data is already kind of filtered, which is yet another reason I didn't worry about being too much of a purist, especially after I found out that even the wind readers, these people like Rob Maher, that running on the flat ground isn't good enough, you have to run up and down mountains, that they walk when they get to a really steep part. So there goes my concern about, we're filtering the data already because, I'm going to walk slower when it's steeper, right? It'll still work. So this is the Google aerial. That's Truman Gulch there. Up the very top there is Ross Pass. Collected a total of 731 data points one way, 4.3 miles, altitude between 65.45 and 77.21, and speeds approaching 4 miles an hour at best. So in this, I'm just doing a direct mapping of speeds to rhythms, meaning the onset, how long do we have to wait before we get to the next note. I'm not quantizing the rhythms in any way, and I'll show you why that's not a good thing for a live human performer. My pitches that I'm mapping those altitudes on are chromatic scale. So if you went up to a piano and you played one key and the next key, the next key, the next key, the next key, or if you're on your guitar and you go from one fret to the next to the next. So as far as normal Western tuning scales go, it's about as close together as we tend to put notes. And that's pretty much it. So this is just the piano roll out of Logic. So you can kind of follow that it does follow that shape exactly. I've done us all a favor and I've sped this up 4 times because, again, if it just goes up and down and doesn't take any left turns now and then, it really is kind of boring. Right about there. Okay. Right, so that's the word. That's fun, but musically not so interesting, right? I also mentioned that I didn't quantize the rhythms any. This is what you would get if you put that into standard musical notation. Again, it's totally playable, but most people don't like to count that hard or practice that much, so probably I should fix that too. So ROS 2 here is kind of the improvements made to ROS 1. What's different? The rhythms are going to be quantized, and instead of that chromatic scale, I mean, sometimes you want that. There are kinds of music, some of the late romantic, very dramatic music, that part of its drama is that you always feel a little unstable, that you don't always know where that ba-da-da-da-da-da-da, you don't always know where tonic is. And when you're using the chromatic scale, you have 12 notes instead of 7 notes, and there's a bigger sense of unease, but I don't know that I want that for the entire piece. So this version of the code, you can actually give a user-defined pitch list. So you could be doing up and down those mountains in C major, or an octatonic scale, or anything you choose. It also interpolates over the pitch list based on your function start time and your function end time. So since this is a music program, obviously a lot of times you're going to want to make a list of data and pull it out one by one by one by one. But it enables you to kind of scale that whole hike up and down the mountains if instead you use time to interpolate. So you may not hit absolutely every data point in that GPS file, but you're still going to get that overall shape like you want. And you're actually going to be able to, make one call to the function. This is actually a sample call to the function here. That you maybe start at 0 seconds, go for 30 seconds. You're going to iterate over the big swoop, ROS pass, the 2 little ones. And then maybe from 40 seconds to 45 seconds, you're going to do another call to the function with different pitches. So makes it a lot more flexible as far as how you might want to choose to make it musical. So here is that with a little left turn here in there. There we go. There we go. There we go. So there's 3 bills in that. Oh wait, there's more. The next, improvement or version of this was everything that ROS 2 does, but occasionally we're going to get notes that are outside this prescribed pitch list. And in this version, I'm just putting them within the body of the code. You could also, of course, hand off some intervals that you want to transpose by. And there's kind of a trajectory list for, the farther in time we are, the chances that we're going to transpose can fluctuate. So you can have, lots and lots of transposition in the beginning, hardly any in the middle, and then lots and lots towards the end again, just to kind of shake things up and make it interesting. The other thing that I found musically not that satisfying about, some of these straight up sonifications was, typically music has some resting points, right? We call them cadences in traditional music. But just some time where you can hang out on a long note and think about everything you've heard and take a little rest, give your brain and your ears a break before you go on. So this one also has a list of longer durations that, again, it's going to pick based on tendency maps or trajectories. So that now and then we'll get a nice long note in there. I actually can't see my cursor on my screen. Yeah, it's making things difficult. Can you see it? Up there? No. Oh, there it is. I really am kind of good at clicking play buttons. So there's an octave transposition there. I didn't put the piano roller score up, but if you look, you do see that you basically have those three big curves, but with some outliers here and there along the way that makes it more interesting. This was kind of like the typical hike that really scared me once I looked at the data, because again, look at that, it goes up and it goes down, and boy, would that sound, pretty boring. So this is the hike up to Highlight Lake. You can actually see on this, you notice how the speed goes way up. That's in the car on the way back to the campsite. Wasn't a sudden burst of insane energy. And you can see on the map, you can actually see the reservoir somewhere. There it is. So the hike starts, I don't know somewhere like here. But we took all the data, because you can always cut it out if you don't want it. So this is almost 2,000 data points. 12 miles round trip, sorry. Altitudes between the mid 6,000s and almost 9,000 feet. I'd hoped to get up to Highlight Peak, but it was still snowed in. This was early June, and there was just really no getting there safely or pleasantly. So in this one, remember how I said if you have a call that has various timings in it, you can actually iterate over all the data points so that you can have kind of multiple iterations of that same basic shape, which, hey, guess what? That's a super musical thing to do, right? To repeat something. Whether it's the exact notes, it isn't always. Sometimes it's just that overall shape or gesture. So, we might be getting somewhere here. Again, I want to give up, offer my apologies. These are obviously raw MIDI files, and so they're kind of machine-like. Yeah, it'll sound much better with Madeline playing, I'm sure. So here we go. So the arguments here are your function start time and end time. So we should hear a little break, another 20 seconds, and then another 15 seconds to end it. These are the long durations that we're occasionally going to pause and rest on based on some tendencies, tendency map kind of things. And these are the pitch lists that we're going to iterate over. So this is just MIDI E's. So 36, middle C is 60, and as you go down the scale, you just subtract 1. So 36 is the low C, it's the lowest note on a cello, 2 ledger lines below the bass clef staff. And it goes up from there. So wherever, and it's indexing into this list so that whenever we get a higher altitude, we're pointing over more to this end of the list, and we get lower altitudes, we're pointing over to that end of the list. fast notes at the end, that's car tone. So it's starting to sound more musical, right? I mean, depending on how you pick these pitches, anybody that ever did band or choir, you can see this is actually just the first three notes of a major scale. Ba-da-dee. So it can be, very musical depending on, or I guess gentler to the ears. I happen to like really dissonant music. But it's all what you put in that list of notes, where you could either make it something that's, completely D major if you wanted, or you could put in something that's more of a chromatic scale, and get, Arnold Schoenberg sounding stuff. So, however you like it. The next bit of data we'll look at and talk about is the Ruby River, which is out past, it joins the Beaverhead just south of Twin Bridges. A really gorgeous river. As you might expect, there's really not a lot of elevation gain or loss. You go pretty much consistently down. And I think it's a difference of 417 feet over 9 miles of river. But the fun thing here really is these speeds, right? So depending on, the kinks in the river, or how fast the current is, you can go really slowly. There's actually a moment, this is the first float trip I've ever taken in Montana. I'm a native Midwesterner, and there were things in the book. I told my sister we should get a book, because around here you could think you're going on a nice float trip and you go over a waterfall, which doesn't really happen in Iowa so much. And they listed all the hazards of particular rivers. And one thing I hadn't thought of was irrigation ditch intakes. That can create some strange currents. And I hit one on this trip that actually just stopped me. Going along and just stopped. I was like, why did I just stop? And then I remembered I was probably about to get sucked into an irrigation ditch. It was scary. So this river is super interesting. Remember, this is the data I almost didn't get. But then I said, sure, just do it. Worst case, you won't use it. Look at this crazy river. Look at how curly that thing is. I love we have like a little horsehead nebula here. The next picture is just zoomed in on that a little bit more so you can start to get an idea. It was a really amazing float trip. I've done lots of them, back in the Midwest. But the thing that, usually you're going down, and if there's mountains here, sometimes you see the mountains slightly over your shoulder, and sometimes you might almost be facing them. This particular trip, you face absolutely every direction at some point during the trip. And I looked at that and I thought, wow. I think I need to play with those headings. So that's what I ended up doing. You get, that's obviously an error of 364 degrees. I don't think that happens. But speeds up to 5.8 miles an hour. The altitude change there, like I said, not a lot, 8.9 miles. So in this, I'm mapping speeds to durations again. And the chromatic scale for pitches onto the headings. So this is like a little sample function call. That's the function name. This is the note I'm going to be on when I'm at 0 degrees. This is the note I'm going to be on just before I get back to 0 degrees. So again, you can name your span, and you could map it onto, maybe only a perfect fifth if you wanted. That would be really boring, but you could. And then again, to give us a little rest, occasionally we might get on to a longer duration. About this is, I think when you map it, remember I said the chromatic scale, you feel kind of ungrounded because there's no resting tone at the scale. That totally works for me for a kayak trip, right? Because it's floaty, it's meandering. I will probably leave this one mapped onto the chromatic scale. Or the other version I did, we're still doing the GPS speeds mapped onto the durations, and we're still doing pitches onto headings. But it's called Ruby quadrants because I broke it up into the 4 quadrants. So that if you're from 0 to almost 90 degrees, you're going to pick these pitches, which again, we have whole step, whole step, whole step. So a whole tone scale. That's when they play when Gilligan's falling asleep. We have 90 to almost 180 degrees is going to play a chromatic scale. The next quadrant is going to play an octatonic scale, which if you like the music of Bela Bartok, he uses the octatonic scale a lot. So that's where you alternate one semitone with 3 semitones. So a minor second, the jazz interval, da 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 da, with a minor third. And our last quadrant here, actually playing a fully diminished 7th chord. So this sounds a little different because it breaks up all the 4 quadrants into very distinctive registers in pitch, right? You can see this is that C below the bass clef, and we get up here all the way into a little bit above the treble clef staff. So again, one of the things I'm going to be working on, a little longer before this thing is considered done, would be phrasing, kind of, again, breaking out of that constant motion just to get us a nice long note that we can kind of pause and reflect on and let our brains rest a little bit. All right, I have to do this. Jason knows this. It has to be a slide with my dog on it. This was really fascinating, and our veterinarian was very pleased to hear this. When we looked at the data, I was telling my partner about how it would be really boring, so I'm going to have to use this algorithmic programming environment to add some kind of jitter, to add little side trips, to say, maybe now and then, if we're at exactly 8,000 feet, I'm going to play this certain motive, things like that. And he pointed out that the dogs are completely insane on a hike. Right? They run ahead 100 yards, they come back to you. Are you coming? They run up another quarter mile, they come back to you. They go straight up the mountain on the side of the trail because they smelled something cool up there, right? So we actually did several examples where we put the GPS unit, we got a nice waterproof case, and put that into these little doggy backpacks that you can have. So this is actually on Ross Pass in the spring. There's the flowers, and the younger lab is using my foot as a pillow, and then the older lab is using her as a pillow. There we go. So this was actually data taken at Snowfill, which I believe, is that no landfill, technically? Does anyone know? Is it? It is. So it's a off-leash dog park. So doggy Disneyland, definitely, all the way. And it's kind of on the bench, leading up to the bench. So there are a lot of dips and hills and things like that. So again, the green is your altitude, which is actually fairly interesting. And then the blue is the speed, right? So we're chasing tennis balls and we're running into dogs. And we have to stop and smell noses and all that kind of stuff. So the speed data in this one is pretty crazy. I probably should be doing a little more with it than I am in this example. But I found, if you've noticed, as I'm going along, I'm finding more and more ways to make this potentially kind of boring data sound fun. So this is the aerial Google Maps of it. What is that? Yeah, you guys know where it is. It's a fun dog park. So that's the circuit she takes. It's a loop trail, and those in green are the altitudes. So it's a 1.5 mile loop. Again, we get about 2,000 feet of altitude change. Speeds, 13.3. That is not me or my husband. Trust me. We max out around 4.8, and that's going downhill. So in this, again, I'm doing a thing where we can take multiple calls to the same function and iterate over those same cool shapes, possibly multiple times, have a little bit of repetition in the work. Altitudes are mapped to pitches. It's not as big a span of altitudes as, say, going from the reservoir up to Highlight Lake. It uses Common Music's cycle feature to cycle through all the altitudes and speeds. So instead of, how I said sometimes I take just a longer list and I index into it based on, where we are in the duration of that function. This one I just use all the notes for now. It's going to interpolate. It's keeping track of the count every time we go through the loop. And it's using where we are through the whole algorithm to determine what are our chances of getting some of these fun, slightly randomized transpositions. So if a random value of transp chance is less than or equal to 1, then we add an interval of between 1 and max jit, which is this number I give here, to that interval. So instead of just following all those same curves, again, we want to now and then take a little left turn and just be a little surprised in music, right? You ever hear music that does everything you thought it was going to do? Yeah, it's not necessarily the best thing. So these are multiple calls to the same function. This is my maximum number of semitones that I might get in transposition based on that tendency. And I made them big for this example so you could hear them, because if you haven't listened to the data way too many times, they might not be so easy to pick out, right? Because it's going from somewhere between adding one semitone, one key on the piano, and this number. So this could be as little as 1, right? Or it could be as much as an entire octave that is added. This is hilarious. Any of you know key command? Isn't that taking the next slide? Thanks, Becky. There we go. It worked out. Oh, that's quiet. Oh, I'm sorry. I turned that one down. It faded out, remember? Let's go back to the beginning. There's that. And then another version of that was, thinking about how we might slightly tweak this data to make it a little more interesting, was to read through the list, not completely straightforward, right? So maybe go from the 0th element up to the 10th element, jump back to the 5th element, go up to the 15th element, jump back to the 9th element, go up to the 18th element. So you're still kind of tracing those curves, you're just kind of tracing and back tracing it over again. So in this, again, this is your function start time, your function end time. These are your segment lengths for how far you read before you jump back. These are how far you jump back. And then here we're giving a list of pitches that, that's many octaves. And then when we get to the end of the list, I'll probably work on that code a little more. But as it is, you can hear it just kind of spirals back as far as it can go because you can't give it an index value that's bigger than the list or it gets really unhappy. So, those last two are probably kind of like the scherzo, the fast vivace movement there. And I don't know if you probably like to take time for questions. That's the last slide I had right there. And then I could possibly show you, so there's going to be the live cellist, and then there's going to be, I haven't decided whether I'm going to do real-time inputting from the cello through a microphone and processing it that way, or do what we call fixed media, where I take pre-recorded sounds and perform various magical transformations on them. I could show you some of the sounds I have, or we could just Do you usually do questions at the end? Okay, question time.
Have you tried mapping the data on the harmonies at all?
Actually, because this setup as I'm making it is so inherently linear, but I couldn't help, I couldn't resist. What would happen if I did, some of those function calls where maybe 3 calls to the function all start at the same time? So yeah, my doctoral thesis was actually a string quartet that used this program. So I was writing out 4 parts. And that's kind of interesting because you can do really fun things with like knowing where you have a dissonance between all the parts and where you have a resolution. I didn't play with it much. I tried to stay focused on the piece, that's due first, but absolutely I couldn't help but stacking up 3 or 4 calls and and I just did it again diatonically because unless you set up a lot of rules, you're bound to get some pretty dissonant clusters and things like that. Which, like I say, I personally kind of like that, but.
But that's one of the interesting things, and I don't know how much the fact that you're doing this for a cello is playing into the way you do the compositions. But a lot of those intervals that you had in there look like they'd be perfect for a double stop or something that you're going to process strings.
Mm-hmm.
So
yeah, I hope so. I also reserve the right to do editing by hand, to make it perfect. And that's definitely something in the field. I actually studied with a man who said, if you don't like the music exactly the way your algorithm spits it out, you need to change your code. And then actually the man that made this algorithmic composition program is like, nah, just fix it by hand, it's cool. So, differences of opinion and technique. And when I was they're like, why does she sound so worried about sonifying GPS data? It's because, I'm sure there are going to be purists out there that, oh, you did what? You added jitter to your pitches, how dare you? You added long notes, how dare you? And I think if you are going to do it straight up, just mapping, and that's the sounds we have, and we're keeping it like that, I think it works really well in, say, an installation, meaning, say, you took sensors, humidity, temperature, ambient light, and you put them out in a beautiful meadow, and you have those transmitted wirelessly into a room, right? That kind of thing, where it's just an environment that you enjoy for however long you have to sit in that room, and then you go bye-bye. But what I'm trying to do here is a fairly traditional concert music piece, where we want to be kind of led on a journey. We want to have spots, like those faster movements where it's all exciting. We want to have spots like the float trip where it's all chill, right? So that's what I'm going for. Yes?
Seems the essence of a hike, at least for a lot of people, are the views.
Mm-hmm.
Have you thought about combining this with GIS, where you would actually then maybe look at distances to where you're viewing as you're going along? So in other words, it sort of becomes multivariate rather than just having a Z instead of a speed. You also have sort of a distance.
Nah, I don't think I've thought about that.
The real question is, can you be multivariate rather than a lot of the things you're doing is sort of the V, looking at the altitude and the speed.
Mm-hmm.
Can you put in an X and a Y?
We can,
factors,
and I haven't done a ton with that yet, but you have other data like your slope, your coverage or course over ground, and things like that I might use to determine other things. It's certainly possible, but for right now, 3 months out, the basics, if you're writing for an acoustic instrument, are the notes and the rhythms. So I was kind of tunnel visioned on that, I admit. So yeah, that would be very interesting to me.
other questions?
I have one more. One of the first things I got is the most patterns of repetition.
Mm-hmm.
Have you or has you worked on detecting a pattern within the data and then trying to have the same musical phrase repeated over that pattern so you can detect more?
In this, no, I haven't done anything like that. But that is definitely something that people out there doing this kind of work are doing. And I understand what you're saying about the repetition. Like I say, my take on that is having the calls that'll iterate over that list of data multiple times, where you are getting some self-similarity. May or may not be exactly the same. As a matter of fact, I don't know that I tried any that would have given you anything too similar, because the way that piece of code is now, you would actually have to have the same pitch list and the same length of call for it to index into the same spots over and over again. But yeah, I know what you mean. And again, that's something I'll be thinking about. Not all music relies as heavily on repeated patterns. And kind of in the tradition, the ways of my people, my musical background, where I came from. At the time I was there, University of Illinois was very much into the avant-garde. Very much into all the pitches, all the rhythms, all the durations. Let's have tuplets inside of tuplets at all times, right? So that's kind of how I think I developed a taste for things that were a little more kind of out there. Although, I'm mellowing with age, definitely. And I definitely like music that's more pitch-centered now, meaning where there is not a tonic the way it would be at a major scale in Western music, but a note where you just hang on it for a while. And I think that's where some of those things where I was adding in longers. Because if I stay on any note long enough, it will begin to sound like a resting point, right? So I'm kind of going for a little more traditional things one way or another.
Thank you, Linda. Grab students, please remember to swipe the cards.